Mm, Put up the chat. So we discussed, like how we can do the stochastic modeling whenever there's a uncertainty, and based upon that uncertainty, we can basically formulate certain scenarios, and for those scenarios, we can do some stochastic modeling, and like the stages will depends upon the specific problem type. Now let's move to like renewable scheduling. So how we can schedule the renewable? So in renewable, like generally we have wind, we have solar, and etc. Others. Now the first question is how it is different from the uh, conventional generation. So the very first is how it is different. Okay. So anyone? Very first point, I think we all know that no fuel is needed. Okay, so which will lead fuel cost is zero. So zero fuel cost is there with like wind and solar. Then it is emission free. Variation in solar light and wind speed are uncertain. Yes, so that is thank you. It is emission free. Okay, and third part is, as mentioned by Satyanarayanan, that there are a lot of variations, or I can call it, or, or uncertainty. Okay, so there are a lot of uncertainty. So hence it is non-dispatchable. We cannot dispatch to a fixed quantity. Let's say like I want to dispatch a wind generator for tomorrow that this much power it should produce, but we cannot do that because it is highly uncertain. Okay, so it is undispatchable, and hence the trading is very risky for our. Just a second. Yes, lot of variation, and as the second point is about like it's emission free, so government provides incentives or subsidies. Okay, government support is there and government subsidies are there to encourage renewable. So as it is non-dispatchable, okay, so it is non-dispatchable, so it will need balancing in real time. Okay, and that basically in real time. So what happens basically? So we have bilateral contracts, then day-ahead markets, and then intraday markets, and at the last we go with the uh, real-time balancing market. So in balancing market is the last resort, right? Here another thing is all the cheaper generators or the cheaper producers has been basically, so like if you look at the market curve, like we initially studied like market clearing. So all the cheaper generations are basically on the left hand side of that curve, and when we do the market clearing, there is a point of intersection between supply and demand curve, and all the cheaper generators has been scheduled from the market clearing itself. So, for real-time balancing market, there will be expensive generators available. Okay. So, expensive generators or generation is available. However, it is dispatchable, because if it is again a non-dispatchable, we cannot balance it with it. So, it is dispatchable as well. Okay. So, generally, we keep them in the form of reserve. Okay, so this is how we basically do the balancing support. Now, what are the different options if I talk about for a renewable or wind power plant? Okay, so let's talk, I will keep renewable is, let's assume wind, because both solar and wind have the uncertainty. But let's talk about like wind. So first option is like different options are available how we can incorporate wind into the our entire system. So first is basically we can include this renewable energy generation as a negative demand. Okay, then if it is just a negative demand, the whatever it will inject, it will be basically going to the system, and whatever is the price, it pays that one. But no, if it is just like a demand, um, the settlement will be at a regulated price, or generally we call it tariff. Okay, so some regulated tariff fixed amount it will get. So what are the benefits? So the plus point for this is no risk is involved, because whatever they are producing, whether it is less or more doesn't matter, and whatever is the time doesn't matter, they will get a fixed price. So whether it is peak hours, let's say in the evening, the where the market prices are very high, uh, it will still get the same regulated tariff. Whether it is, let's say, early morning where there is no load, and market prices are very less, it will still get the same tariff, and usually the tariff will be low. So plus point is no risk. What are the minus points? That it will lose the, so loss of opportunity to make higher profit in different markets. Okay, so it will lose that opportunity, that yes, if it goes into the market, usually the prices are higher, and there it can make lot of profit. So that is one thing, that it can be treated as a demand, and just a regulated tariff it will get. So that is first part. Second part is uh, this renewable generation participate into markets. So by means markets, I'm talking about like day-ahead and intraday market. So different time frame is there. So it participate into different markets. But as it is going into market, uh, obviously it cannot be dispatchable. So let's say if a renewable generation participates into day-ahead market, uh, schedule will be prepared in the day-ahead fashion, one day before. So once the schedule is final, either it like at the time of delivery, either it is less than the schedule or more than the schedule. If it is less than the schedule, it has to pay the deviation charges, and if it is more than the schedule, uh, again if it is very much like very high percentage, it has to pay again some penalty, and otherwise the money it will get will be lesser. So that is the issue, that it has to pay the deviation charges. So but uh, phase deviation charges, okay. But we can say that some subsidy will be provided, some subsidy to support, okay. So if some subsidy is provided, I can say the profit will be whatever is the market price and whatever is it has been scheduled. So let's say some market price is there, some schedule minus whatever is the deviation charges and plus some subsidy. So whenever we are providing this subsidy, we are basically not into a perfectly competitive market. So another option is pure competitive market. And in pure competitive market, basically it will participate in the pure competitive market and no subsidy. So there are option like all of these three options has been there, and we have seen it as well. So initially when we don't like, so right now we have lot of renewable with us in our grid, but initially when we were increasing renewable like both solar and wind, uh, we treated these generations as a negative demand, that okay, if you want to install a renewable power plant like wind power plant or solar farm, you basically whatever you produce you just inject it, and based upon the meter reading we will pay you some fixed price, plus subsidy was there as well. Then but as the renewable is increasing, it is uncertain, and to basically manage that variations in the real time, it is very difficult for a system operator. So they have to keep a lot of reserve to basically balance out or meet out the uncertainty of the renewable in the real time. So that cost is basically you can say, if we go with the option one with the regulated tariff and no penalty, nothing at all on the renewable, then uh, those has to be borne by other players. If we just simply talk about, because money will come from somebody if we are compensating somebody else. So yes, it has to be borne by some the other players, either directly or indirectly, okay. But as the renewable share is more, the reserve requirement will be more. So the first option is good when we have very less renewable in the system. So let's say like when we started integrating renewable, at that time the first option was very much good and feasible as well, and it supported the renewable integration and as well as the grid, okay. So because some generation is available at free of cost, and so only very less amount has to be paid for that, okay. But as the renewable share is increasing, it should or it have to participate in the markets. But again, if renewable generation participate in the market, because of their volatility and this variability, uncertain nature, they will face a very high deviation charges. So that's why government basically should support them in some form of subsidy if it is very much high. But if we talk about, like what is the last resort, or after a certain integration, like in Denmark, I think they have more than 90% integration. So there you cannot provide subsidy because the entire generation is basically renewable. So who will you cross subsidize to provide that subsidy? It's always subsidy is not like giving up money. It is basically taking from somebody to giving it somebody else. So in pure competitive market, there will be no subsidy. In that case, uh, so that third point basically we are interested, or even second as well, because the subsidy is kind of fixed. Okay, so we are interested in the second point. Now, how the balancing market works, and like what are the different scenarios. So let's set up that one. So let me define two different prices. One is like up regulation price. So it is basically price for positive deviation. If you are deviating positively, then you will get this particular price. Okay, and then if prices are lambda minus, that is price for a negative deviation. So let's set up these two prices. Now let's calculate what will be the deviation charges. So I'm just trying to formulate, like very basic picture that what will be the objective for renewable. Can anyone? That let's say wind power producer is there. What objective it should have? Like what is the like goal of a renewable generator uh, who wants to participate in the market? Yes. So everybody wants to maximize the profit. So that is the objective. So how will you define profit? So there is always yes, profit maximization, revenue maximization. So I can define profit is whatever is money I'm getting. So that is revenue, and whatever is the cost I'm facing. Okay, so that is my profit. Or like let's say a thermal generator, if we talk about, it is getting some money, and it has certain cost as well for producing. So that revenue minus cost will be the profit. We have assumed that there is no fuel cost associated with renewable. Only certain fixed costs are there, like labor cost and some capital cost. So the interest will come for that capital cost and maintenance cost. So that those are basically not power production dependent cost. They are basically they does not depend upon the P, or whatever is the power output of a renewable generation. So I can assume that this is zero. Okay, so profit is nothing but the revenue. We can assume, one simplified form. So I can say that the objective will be maximization of revenue, and that will be equals to, let's say it is participating in the day-ahead market. So in the day-ahead market, and whatever is my basically day-ahead participation. Uh, let's assume at any like if we are talking about the 24 hours, so we will add it up from 1 to uh, capital T. It can be like depending upon the time period, it can be 1 hour, it can be uh, 15 minutes block. So that is capital T, and then this is like PD plus some imbalance cost it has to pay. Okay, so now what is imbalance cost here? So first of all, let me put down some conditions. What are the conditions basically? So first of all, this PD, whatever is we are getting scheduled in the day-ahead market, it should be within the maximum capacity of the plant. Okay. Now another part is this imbalance. So how can we calculate imbalance? So first of all, we will see that what is change. Okay. Now the input here will be like wind producer will also have certain forecast that okay, this is my forecast for the tomorrow, and from for that forecast it will have. So let's say this is forecast, and let's say at a particular time t, and out of that forecast it has bidded that okay, let's say 50 20 megawatt was the forecast. Let's assume a very large power plant. 50 megawatt was the forecast, and in the day-ahead market, it has been scheduled that okay, you can produce 40 megawatt. Okay. Now the thing is, it has been scheduled 40 megawatt, so 10 megawatt is extra, but it is not sure that 10 megawatt will be available there or not. So it is again a scenario. So we can basically there will be different scenarios. So we will talk about not directly in terms of whatever I have written here. We will talk about in terms of scenario, but just to understand the imbalance cost, what we have to do is we have to define this imbalance cost at any time t equals to two part. One is we have defined some prices lambda. So if this delta t, and it is when this delta t is positive. So if positive deviations are there, it will face a penalty of this, and if it is minus, then it will face a penalty of this. Now somebody can question that sir, whatever is the deviation, it is basically being added into the here, like we are adding it here, right? So how it is penalty? It should be reduced. Penalty is the cost should be reduced, right? So let's try to understand this one. Let's say the PD schedule is 40. Okay. Now there are two scenarios where this deviation can be positive. So let's say one scenario that some realistic production at that time is 50, and let's say the production may be 30. Okay, so like real time production can be 50 or 30, it's uncertain, right? So here it has been scheduled 40 only in the day-ahead market, but it is producing 50 megawatt. So if it is producing 50 megawatt, the 10 megawatt, it has to get some money. So that's why it is getting or basically I'm saying we are adding a lambda plus into 10. This is the addition in the revenue. So that's why it is added. Now, if it is less, I have defined delta t like this. So this delta t will be negative. So if it is negative, it should be subtracted. So yes, this is minus t, and this value is minus 10. So this overall basically this value is going to be subtracted from the whatever we are basically having the revenue in the day-ahead market. So that's why it is called imbalance cost. So you will get some money if you produce more, whatever schedule, and if you will get some, you will lose money definitely if you basically do not produce uh, the whatever it has been scheduled. But it is not simply like that. That still we can call this first part as a revenue. But let me tell you one thing. Usually what happens that if you look at these prices, let's say market is settled and you so power balance is there, some price has been decided from that power balance. So one price is already there and let's assume that is market price, and in this particular case let's assume lambda d is the market price. Now in that equilibrium condition, if you inject more, what will happen to supply demand balance? Supply will be more and demand will be less. And as we like already covered that whenever there is a more supply and less demand, the prices will go low. Okay, so prices will go low, and whenever there is a opposite like lambda minus, if I talk about, we are basically negative deviation. So whatever we have scheduled, we are injecting less than that. In that case, we are making a supply deficit case where demand is more and supply is less. So prices will further go high. So I can assume here that this lambda plus is less than lambda minus. Okay, this is one of the condition. So this real-time price basically can be less than the day-ahead price and it can be more than the day-ahead price, but whatever is the real-time price, it will be close to that, and that's why it will basically lose its value. So that's why it is called imbalance cost. Now let's talk about different scenarios, like we were talking about the stochastic modeling, so let's discuss it. So like in above formulation, the we have price which is uncertain. So what are the different uncertain parameters? So first is price, second is renewable production, and third is so price, which means like both day ahead price and real time price, both are basically uncertain. And then we have renewable production, which is also uncertain. Now one thing is here, like as this simply like we have discussed that renewable does not have any cost. So if it does not have any cost, what it should bid into the market? तो कुछ cost ही नहीं है that that okay, I'm going to charge you at least this much. So that at least this much is basically will come out from the cost function, that okay, it has certain cost, so it should get at least this much money. So how it will decide the bidding? It is zero. So whatever money it can acquire from the market, that is good. Okay, otherwise that wind is flowing, you can produce something, and if you are not able to inject that, it's a loss. Okay, so it's a, again like at that time it's loss. So whatever, even if it is 1 rupees, why not take it, right? So there is no cost. So generally we this kind of players where no cost are there, they cannot affect the market. And we discussed price maker and price taker. So this behave as a price taker. So they simply inject into the market, and whatever is the market price, they receive that as it is. Okay, they do not affect the market price, and whatever is the market price is there, they take it. So if they cannot affect the market price, like economic dispatch we talked about, market based economic dispatch we talked about. Here basically that economic dispatch in a way gives a system price. So if there is a like cost function, then it can lead to a system price. Otherwise what happens that uh, if cost is zero, there is it will not affect the system price. Whatever is the maximum value, it will go to that. If we solve with the economic load dispatch for let's say wind producer. Okay, because the cost is zero, so they are price taker. And whenever there is a price taker, we do not perform like scheduling problem or market clearing, it is called self scheduling, that they have to schedule themselves, that irrespective of the market they are going to produce, so they have to schedule themselves that okay, this is this much I'm going to produce. So the quantity is the only issue for case of renewable. Price is not right now. So it's basically like whatever money they can get out of market, it is fine. So they have to self schedule themselves in such a way that this imbalanced cost is minimized. It should not be more. Okay, so I will put down the detailed formulation, like let's say the maximization of certain values. So let's say there are different scenarios. Okay, so we have like earlier in the morning we discussed like different scenarios will be there. So there will be like wind power scenario, real time price scenario, and day price scenario, and we club them together. We will receive we will have many scenarios. So let's say the summation over all the scenarios. Let's say summation over all the time periods. Okay, and phi w is the probability of a scenario. So if I multiply probability of scenario with the revenue, so the revenue will be whatever is the lambda d for any time t and for any scenario. So this has been already defined that okay, this will be the input. Then we have to identify what should be my production in that particular time over all scenarios. So there will be multiple scenarios, like one scenario is saying that there is a 20% probability of high renewable generation tomorrow, maybe 30% probability that there is a low probability of the production tomorrow, and 50% probability is that with this much medium moderate production will be available. So we have to optimize over all scenarios of these probable scenarios, and this is my decision variable. So I will put it here under max, that this BDT is my decision variable or output basically. So this is my revenue plus, if I have been scheduled to certain PD, that okay, this is going to be my schedule, I have to look for the real time scenarios as well, that okay, if real time scenarios go sideways, how much imbalance cost a wind producer or the renewable producer is going to face. So this is imbalance cost at any time t and for any scenario. So this is the basically objective function. We are trying to maximize the revenue plus the imbalance cost. Imbalance cost is also like revenue positive deviation and minus or negative whenever there is a negative deviation. So this is called expectation of revenue, because we are doing the weighted sum with the probability. So that will basically average out everything. Okay. Now, if I look at the conditions, subject to conditions, what are the conditions? So first of all, let me define this ICTW. Okay, so ICTW is basically, it has two terms. One is lambda plus, and this is real time, like possibility that it will face a lambda plus. Okay, and then some deviation in a particular time and scenario. And whenever there is a this deviation is positive, then we will face this price. And minus tw is basically if it is negative, and negative means this entire term will become negative, and that will be basically, instead of addition, it will be subtracted from the objective function. So if delta 2 is negative. Okay, so this we have to write down for all the time and all the scenarios. Okay, so this is the very first condition. Second is basically our PDT, like whatever schedule we are trying to optimize, that okay, this is what this is the schedule I should get, self scheduling. So this is my variable. This should be whatever is the maximum like production level, and this I have to calculate for all the time t. Once it has been obtained for all the time t, I can say that okay, I have optimized in such a way that I'm able to maximize my revenue and the imbalance cost, and whatever is the PDT, that will be the schedule. with the maximum profit. So this is PDT. Then if we define delta TW, that what is the deviation? So deviation is like, let's say some realization is there, like some forecast or some scenario for wind production is there. So that forecast is there, and that is again at every time T, and for scenario W minus whatever is the schedule. So this forecast can be positive, and this forecast can be more than the schedule, it can be less than the schedule. So based upon that, this imbalance delta TW. So this delta TW is basically, I can call it imbalance. That's why I have named it imbalance cost. Okay. So this imbalance is can be positive and negative, and this we have to calculate for all the times and all the scenarios. Okay. If you have any doubts, please put them in the chat or raise your hand. We will take them. Then, if I look at this equation, both of these conditions, I can put a limit on delta TW, maximum and minimum limit, and by looking at this PF and PTW, I can put a limit that the delta T can be maximum value of whenever this part is 0. So if this part can be either 0 or Pmax. If it is Pmax, this part is Pmax, then delta TW will be not at maximum value. So if this PDW is 0, then delta TW will have maximum value of this. So I can put a condition that this delta TW will have a maximum value of PF TW. Similarly, if I look at the minimum condition on the deviation, whenever this PDW is 0, uh, and PFTW is 0, and this PDTW is at maximum value, that value will basically be the minimum value of this particular uh, imbalance. So I can put it, and that too with a minus sign. So whatever is the Pmax, that will be the limits on the imbalance. So I can write down these for all the time and scenarios here. Okay. So once it has been defined, let's assume okay. Now one question is, can we optimize this one? So far we have learned, like F-min con, we have learned linear programming, quadratic programming, NLP. Sir, when MNRE reintroduced reserve auction, isn't it minimizing revenue for the renewable? Satya, I have, and I think I am not aware about the reserve auction, but it's not never like the objective can never be minimization of revenue. Like you cannot penalize anyone. That is against the market. So you can never penalize. So basically, if you are minimizing revenue, it means basically you are just keep that unit shut. Keep the power production equals to 0, revenue will be 0. Okay. So it's never like minimizing the revenue. Yes, they can minimize the risk associated with it. So about that we will talk about, but it can never be like minimization of revenue or minimization of profit. If you have how the imbalance cost reflect in LMP calculation? No, it does not reflect in the LMP calculation because as I told you, this renewable is basically a price taker, so it cannot uh, define LMP. It's a basically as 0, like cost is 0, so it is no longer equals to the like incremental cost. There is no incremental cost associated with it, and as we have seen in economic load dispatch, the system price is equals to the incremental cost of a generator. Okay, so it will not affect LMP. it can reduce LMP because the um, prices are basically whatever in the system. Okay, so uh, let's discuss it, like the market one. Okay, wait. Okay, I will put it here. So let's say there is a supply curve and there is a demand curve, and this intersection point is basically the market clearing price. And we cannot visualize LMP just with like this simple example, but let's say it's a price. LMP is also a price at nodes, and MCP is also price at all the nodes when network is not there. So let's keep it. So this is supply function, right? Supply function says that you are getting power at certain price, and based upon that we have built this particular supply function. Let me okay, let's keep instead of the curve, let's keep only one generator is there and one demand is there. So that generator, instead of bits, it has a linear cost function. So this is a supply function, and this is, let's say, demand function. Okay, now this one generator, let's say this is a generator A, which has this kind of bidding curve, linear bid curve. So this will be my market clearing price. What happened here? What will happen here, that a renewable generation wants to win. Let's say a renewable generation with zero cost or zero bid, price bid, wants to enter into this particular thing. So now we have two generator. Let's say generator A is basically some B plus MP. So this is B, this is slope M, and P is the production. Okay, so this is a generator 1 and a generator B, which says that okay, cost is 0 and I can produce some P. Okay, so this P is basically, and this is the cost function. So and certain limits are also there, and we are assuming it's infinite. So yes, many thing is many are whatever quantity we want, we can basically get it from this generator A, and generator B has certain limit that okay, it can produce certain. Let's keep it. Let's say PW, wind producer it is. Okay, so let's say PW it can produce. So I have to redraw the supply curve. So now two generators are there. So I have to stack these generators in order of a cost. So like least cost will go in the very first. The cost is 0. So my supply curve will start like this. On the 0, I will draw it like this up to the PW power. Then I will have this supply curve. So this is our wind producer, let's say, and this was our generator A. Let's say this is our wind producer, and we have the same demand curve, which is like this. So this will be the MCP. So actually what we are doing is we are shifting this entire curve in this particular direction. This is what we are doing. So I can redraw this particular diagram here in the above and overlap it. So this is PW of wind producer, and then I get a I can draw this generator A supply curve. So you can see the market clearing price has been reduced. The intersection point has been reduced. So the renewable, yes, will uh, reduce the market clearing price, but it can never set it. So the price will be set by uh, this particular demand, and this particular generator's cost curve will set this particular price. So it can never basically define or set the market price, but yes, it can affect the market price. So this is how we can understand it. So that's why I'm saying that renewable generation is, let's assume we are talking about the perfectly competitive market where nobody can everyone is very small as compared to the system. And if everybody is very small and large number of players are there, they cannot affect at all. Basically, it's a perfectly competitive market, so that quantity will have no significance. In this particular example, yes, that quantity will have significance because we only had one generator and we added another one, but otherwise it is price taker. So imbalance cost can never be reflected in LMP calculation. Okay, and it is self-scheduling. So whatever is the doesn't matter. It is not part of market clearing. It is self-scheduling. So renewable is performing this action its own at own level, and it is no longer part of market. So yes, it has nothing to do with the LMP calculation. Now, yes, we were discussing about like what is the nature of this particular problem. So if you see, everything is linear. Like here, this pi w is input, lambda d is also input, pd is my variable, so it is linear. This incremental cost, if I look at, this is lambda plus is input, and delta tw is also a single variable, so it is linear. The incremental cost is also linear. And if I look at the this particular constant, linear, imbalance cost is linear, and everything is linear. But the issue is this conditional expression, this particular part, this has a condition. So if we try to solve this condition, what we have to do is we have to assume, let's assume like a some discrete variable, that if this happens, if one thing happens, other can never happen basically. So what we will assume that whenever this thing, let's assume a binary variable y, okay, and ytw. So with like with tw is the subscript like I'm using. So this y variable I am using, and it is 0, and either it can be 1. Okay, so let's consider this particular part. If we consider this particular part, what we can do is we can define this imbalance cost in some different way. So here I'm going to define it. Okay, so this imbalance cost tw can be defined by lambda plus tw, delta tw, and 1 minus y. Okay, let's put it like this. So whenever value of y is 0, so we assume that okay, this is the case when ytw is 0. When a y value of ytw is 0, um, this will come into picture, and we will get the imbalance cost of the same. If value of ytw is 1, this term will be 0, and this entire term will go out of the imbalance cost. Then we will put plus lambda minus delta tw and ytw. Okay, so if ytw is 0, second term will be 0, and only first term will be a part of imbalance cost. And if ytw is 1, the first term will be 0, and second term will be the part of the imbalance cost. And it reflects this particular condition very well. Okay, so this entire condition can be written like this. Okay, but here this y is also a variable that it will depends if this imbalance is positive or negative. If it is positive, this y has to be 0. If it is negative, then it has to be 1. Okay, so we have to define that as well, that we don't know whether the, because it's a pd is variable. If this pd is variable here, if this is a variable pd, this imbalance is also variable. And if imbalance is variable, then it can take positive and negative, and I can never say that whether the ytw at any time and for any particular scenario, whether it is going to be positive or negative. So this y has to also change accordingly, and it has to be 0 and 1. So how we can define that basically? So this can be defined like this, that delta TW is basically less than some very big value and 1 minus YTW. And I have defined that minus of delta TW is also less than from a very big value and YTW. So I have kept these two conditions as well. That now let's look at from this condition, imbalance condition from here. If I want to look at these two equations, I don't know what is the value of PD. So if it this lambda TW can be positive and negative. So let's say if lambda TW is positive, okay, if it is positive, look at the both conditions. So let's say lambda TW is a positive value. So if it is positive, my y should become 0. Okay, so this implies that y should attain a value of 0. And if delta TW is negative, my y variable should get a value of 1. If I use these two conditions and let's check. So let's say delta TW is a positive value. So I can say the condition is some positive value is less than a very big value and 1 minus YTW, and some positive value of delta TW. So and let's say the positive means let's say 5. Okay, so I can keep it. 5 is less than something and minus 5 is less than a very big value and YTW. Okay, so it satisfies both the ways. Both the conditions are being satisfied here as well. So like if value of y is 0, still it satisfy. So now check that I try to solve these two conditions. What can be the value of y? So let's say YTW is, if it attains 0 value, what will happen that the first condition will become 5 less than 0. Second condition will become 5 less than 0. Oh no, sorry, very m value. So this is m1. Okay, and another value is basically minus 5 less than 0. Now if YTW is, let's say, 1, so it will become like 5 is less than 0, and another is minus 5 is less than very big value m2. So this is not satisfied, this is satisfied here. So it means that if delta TW is positive, YTW can never be, this will never happen, and this can happen. So it means that whenever delta TW is positive, our YTW will be 0 if I use these two conditions. Same if delta TW is, let's say, negative. Okay, and let's consider minus 5 is the value. So I can write down these two conditions same again. So it is minus 5 less than m1, 1 minus YTW, and minus delta, so that will become plus 5 and less than m2 YTW. Now check again what value it will attain. If let's say YTW becomes 0, I will get a condition of minus 5 less than a very big value of m1, and this will become like 5 is less than 0. So this is not possible. So this can never be happen, that YTW can never be 0. And if you put like 1, it is basically minus 5 less than 0 and 5 less than very big value. So this can also happen, and this is also true. So this will always happen whenever there is a negative imbalance. So I will, my YTW will be 1. So these two conditions basically uh, defines that whenever there is a imbalance of positive, I will always have value of YTW equals to 0, and whenever there is a imbalance negative, my Y value will be 1. So I can put these two conditions. Okay, and I have defined imbalance cost here as well. So if I put everything back to the or our original function, we will basically rewrite the entire formulation like this. So let me change the color again, red. So it was basically a maximization of, and my variable was PDT, maximization of expected, let's say, profit, and summation over W, summation over time. Okay, and then we had a scenario omega, then lambda D, and TW PDT plus lambda plus TW. So this imbalance cost function I will use here. So this imbalance, instead of like whatever we have used here, this imbalance cost, I will use this particular function. So that is lambda plus, let me see, delta TW 1 minus YTW, and plus lambda minus delta TW YTW. Okay, and the entire thing is done. Subject to, we had a certain condition, and the very first condition was the conditional statement, right? So this conditional statement was there. So this condition basically from this particular equation we have placed it here in the objective function, and so we can get rid of this particular equation because we have placed it in the objective function, otherwise it is nowhere. So that we have already placed here. Okay, now the rest conditions were basically that our PDT should be less than P max, and what was the other condition? Delta TW. Yes, so this delta TW was defined, and that was equals to whatever is the PF TW minus PDT, and then we had certain limits. So this has been defined, but to define this YT, I have to place these two conditions as well. So these will also go here, these two conditions, and I will put them here. Delta TW is less than very big value of 1 minus YTW, and minus of delta TW should be less than of very big value of YTW. So these are the two conditions. Apart from that, I think we had one more condition, which is this one. So I will put it here like P max less than delta TW less than PF TW. So this is my now new formulation. Now, if you look at this particular formulation, earlier there was a conditional condition. Now we are no longer have that particular condition, but the issue is this y is also variable, this delta t is also variable, so it becomes non-linear. Okay, so the entire formation become non-linear, and then how we can solve it? That is the big question mark. So let's define that how many basically conditions we have so far here. So if I name it equation number 1, and this is, let's say, obj, equation objective function, this is 2, this is 3, 4, and 5. So these are my different conditions, right? Now if you look at the condition number uh, this 2, so the condition number 2, condition number 3, and condition number 5, if you can see, you can basically merge them together. Okay, so oh sorry, uh, 3, 4, and 5. So it is uh, 3, 4, and 5. So by looking at these conditions, what I can do is I can make a new condition, and that is basically minus P max YTW less than equals to delta TW less than equals to PF TW 1 minus YTW. That these values basically this first condition 3 and 4. So if you just put out 3 and 4, I can write it down like this, that delta TW should be less than M1 1 minus YTW, and it should be more than, if I multiply it, it becomes minus M2 and YTW. So it is like minus TW is more than that, so it is sorry, no minus, it is plus. So 3 and 4 will look like this, and if you compare this with a particular equation number 5, you can get the values of M2 and M1, and that was basically minus PF max and PF TW. So this is what we have placed it. So we can replace the equation 3, 4, 5 with the equation number 6. So if I add 3, 4 and 5, I will get condition 6. So I can reduce the formulation. Okay. Now another thing is here, very important part is I can define certain equations. So like I end up with like set of equations which are available so far is basically first is delta TW equals to PF TW minus PDW, and another equation was this one which we have defined, y max YTW less than delta TW and PF TW 1 minus YTW. And apart from that, we had another condition that this is PD TW less than equals to P max. So in the entire objective function, we have equation 1, so we have written it down. Equation 2, that is also we have written down, and 3, 4, 5, we have merged them and placed it here in this particular equation. Okay, so if you look at these equations, I just made a simple modification, and so one objective function was also there where IC was basically defined lambda plus TW delta TW 1 minus YTW. So this was the term in the objective function. So if you look at this imbalance cost term is here in the objective function. So I am just keeping the lambda dPd and just taken out the imbalance cost and placed it here, and plus some lambda minus TW and delta TW y TW. So this is one thing. I have some simplification. So let's say I made certain assumptions that it is lambda plus. So I have incorporated two different variables. Okay, and one is lambda plus and sorry delta plus, and another is delta minus. And I kept a minus sign instead of this plus sign, if you see. Okay, so I have used these, and based upon that, I can define that delta plus TW is uh, so M1 M2 is very large positive values. So M1 and M2 are very big positive number. Okay, so sometimes this kind of relaxation is also called big M method. Okay, so this kind of relaxation we generally call it big M method, where M values are very large positive values. So here, if you look at this is delta plus. So delta TW 1 minus YTW, and delta minus TW is uh, this particular value but with a negative sign. Okay, so uh, delta t w y t w. Okay, is this clear so far? Now if you look at sorry, minus sign has to be there. Okay, so then yes, thank you. Then we can define delta tw equals to delta plus tw minus delta minus tw, and if you solve these two equations, you can get it. Okay, you can simply basically y tw will cancel out, so we can define like this, and then we can define that what will be the limits on these variables. So I can say that this delta plus is a positive number where the maximum value will be pf tw and 1 minus ytw, and similarly it is delta minus is also a positive number where the maximum value will be p max ytw. So these two are basically so we have defined that imbalance is equals to two positive difference of two positive numbers. So here what we have defined is that the imbalance is like delta plus minus delta minus term. So both of these delta plus and delta minus are positive numbers we have defined, and difference of positive numbers can be positive and can be negative. It depends which number is bigger. So earlier if you see our this particular equation is basically this delta tw is basically negative and positive as well. So but here what we have defined is that it can have a positive basically both the variables delta plus and delta minus, like imbalance positive and imbalance negative, both are positive, and we have defined it like this. So the conditions we can put is from the same, that like this is the condition pf 1 minus y is maximum limit on the positive number, and negative of this value will be the limit on the negative imbalance. So this is what we have basically done so far. Okay, now if you take out this particular condition here, then use basically another condition which is where I have defined it. Okay, let me bit zoom out. This particular one and these two conditions. What I can do is I can write down that delta plus tw. So here this delta tw is equals to delta plus minus delta minus. So I can write down that this is delta minus tw and it is equals to whatever is our power tw minus pdt. So pdt is not with w because it is decision in real like day-8 fashion. So it is first stage variable. It cannot have the only time is there, omega is not there. So this is the first condition we can obtain. Now once this condition has been obtained, so another part is we can basically, so we can merge them and obtain this particular one, and this condition are basically 0 and delta plus tw and whatever is the pf 1 minus ytw. So this we have already defined, so I will put it like this: 0 and delta minus tw and whatever is the p max y tw. Okay, so this is another condition, the same v1 kept here. Now the third condition was this, so I will keep it like this: 0 is less than pd t and p max. So I have obtained equation 1, 2, and 3. And this imbalance cost is basically part of our objective function. So I will define that it is basically uh, IC is basically lambda plus and delta plus, and TW I will place minus lambda minus TW and delta minus TW. With these new set of conditions, I can redefine. Okay, with this, am I audible? Some notification was there. Huh? I'm audible, right? Because I got some notification here. So I can rewrite this entire or revert the entire formulation, and how we can write this, that it is again maximization of expected profit, and that is over scenario over time. Okay, then probability of omega, then we can whatever is the revenue we are getting from the day ahead market. So this is day ahead revenue. Okay, then we have certain imbalance cost, so that was lambda plus, and then we obtained it like delta plus tw minus lambda minus tw, here as well tw, and then some delta minus tw. So if you look at this objective function, it is linear. You can clearly see that PD is a variable, delta plus is a variable, and delta minus is a variable, and rest of them are parameters. So the objective function becomes linear as compared to the earlier one, where the integer y variable was multiplied with the in the objective function, and making the degree equals to 2, and making it non-linear. Now the we will use this lambda. So I will write down without tw, just to keep it short. So tw and tw equals to our whatever is the forecast minus pd t. So this is one condition. Then we have limits on delta plus tw, and then limits on delta minus tw, which is p max and y, and then pf tw1 minus y. Apart from that, we have one thing is which is pdt, which is less than equals to p max. If you look at this particular formulation, it is completely linear. You will see there are different variables. Okay, so this variable is just multiplied with a parameter for a particular scenario. So this is also fixed. This is also linear, this variable, and this variable is also multiplied with a parameter. So objective function is linear. If you look at the degree of these variables, which are I have highlighted with a different color underscore, is 1. Here it is 1. Here ytw is variable, but the multiplier is constant. So again, this is also linear. So this tw is basically constant. So still it is linear because we have shifted it. This is linear, this is linear, and this is also linear. So the entire formation is linearized, and we can call it basically, like one y variable is there, which can be binary basically. So y variable is basically either 0 and 1, and other variables are continuous. So we call it MILP formulation. If you have any doubts, please ask me. Okay, so if no doubts are there, le- uh, let's see some interesting thing. Or should I stop here for this particular part and move on to the next thing? So let's keep it here only, and let's not go into much detail. And okay, so we can further basically get rid of this linear variable and convert this MILP into LP. But let's not go into that part. Okay. Now, what are the basically? So far we have discussed about different scenarios and different values are there. So we were trying to like we have formulated it, but still uh, like you look at the objective function, it is trying to maximize the revenue in the day-ahead market, then plus the revenue from the real-time market for extra injection whenever the deviation is positive, and then uh, it has basically certain cost if it is basically producing less as compared to the schedule. And by solving this, renewable generation can self schedule itself, and it can basically whatever is the PDT variable, it can obtain it. So over the entire day, it can get a demand function that okay, this is going to be the demand, and we can solve it. This is so far, like uh, a risk. So this kind of formulation are called risk neutral formulation. Okay, so these are called risk neutral, that we are not calculating any risk value here. So let's talk about risk measures. Okay, so there are different risk measures available, like by which we can calculate the risk value associated with any uncertainty, or in general, like over the different scenarios, what can be the risk. So very first is variance, then there are two less common variance basically measures. One is shortfall probability. Yes, I'm going into there. Thank you. CVR is one of the risk measure, and then expected shortfall. Then we have value at risk. Generally, we call it VAR, and then we have conditional value at risk. So that is called CVAR. So these are different risk measures. There is certain formulation of these, so we will talk about that. Before that, we will discuss what is the significance of time, like how and what does this signifies. So I will just take a small, break of 1 or 2 minutes, and then I will again come back. I just ask you, do not please don't leave the meeting, and you can also take a break in a meanwhile, like 1 or 2 minutes, and you can have some water and all, and we can rejoin again. Okay. So these are different risk measures, and as we were talking about, like how what are the significance of these. So let me draw a curve. What does this curve signifies? Like what does this curve hold? This curve is basically, we call it bell curve, right? And it represents a normal distribution. Usually, it represents randomness in nature. So, in nature, all the things are random, and usually they follow this kind of bell curve that certain values are mean. So, there will be a certain mean, and some probability will be there. So, the probability of the average value is highest, and then getting a something less or something more than the average value will have kind of equal probabilities. So here as well, like for wind power producer, we can say that there are three different random parameters. One is price, another is your dead price, real time price, and basically power generation. They also follow some randomness, and they will have certain graph, not maybe not exactly like bell this bell curve, but yes, they will have certain graph. So but just to understand these risk measures, let's say this is profit on this particular axis, and here is the probability. So this mean value is your expected profit. This is your expected profit, and all over above is basically like, or even earlier in the morning we were calculating the expected profit values only, or expected revenue or expected profit itself. So like while solving the above formulation which we have discussed just now, it will give me this mean value basically. Okay, now the variance is basically like how much we are deviating from the mean value. So I think we all know what is variance and standard deviation. So variance is basically how what is the degree of like moving, or basically we are short of or more of the mean value. So if this mean value or the variance is less, that is good for the the scenarios, basically uncertainty is less in that case. So by variance, like measuring the variance of the output, we can calculate whether the uncertainty is more or less. If variance is high, we can say there will be the outcomes will be highly uncertain, or uncertainty is very much high. And if we say that variance is low, then we can say the uncertainty is less. Okay, so that is one thing. Then the second part was like these two shortfall probability and expected shortage. They are very less common. Generally, like while doing our engineering studies, we talk about variance, we talk about value at risk, and we talk about CVAR. Usually, we do not consider them because VAR and CVAR has the properties of shortfall probability and expected shortage. But just to give you a picture, what is the shortfall probability? So shortfall probability is basically probability of profit being less than a predefined value. So let's say I have in this particular part, I have defined a certain value. Okay, let's say this is my predefined value, sigma naught, or yeah, let's say sigma naught is my predefined value. So if profit is less than, so it is less than for many points which are available on this particular graph. So if I add them up, that will be my shortfall probability, that what is the probability of profit being less than a predefined value. So if this probability is less, it means my profit will be at least this predefined value most of the times. Okay, so that is the significance of it, that if shortfall probability is more, it means most of the time my profit will be less than whatever a predefined value. So a decision maker can decide that, okay, by doing this entire self scheduling, I should get at least this much profit. So they can come up with a profit value, a predefined value, and once that value is defined, we can calculate the probability, and that will give a picture that, okay, what is the probability of loss, because if uh, the profit is less than this value, we can consider them as a loss, and if it is more than, we can consider them as a profit. So what is the probability of loss, and what is the probability of having a profit more than the we have different cost, and also we expect certain profit value, so that this value is that. Then as third measure is expected shortage. So expected shortage is basically uh, what is the profit or expected profit. I would not say profit. Expected profit uh, for these scenarios. Like, so let's say this is, let's assume scenario 1, scenario 2, 3, scenario 4, and scenario 5. So like I have drawn some certain scenarios dots here. So let's say these scenarios are producing a profit less than a predefined value. So what is the total probability of being profit for profit being less than this particular predefined value? So that is shortfall probability. And then what is the expectation of these profits? So these scenarios will have a profit over here, 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 and these 5 profits will be there. So the mean value of this will give you the expected shortage. So let's say if I go with the uniform, somewhere here will be my expected shortage. So this is the average value of profit being less, and this much value will be the less as compared to the our predefined value. So this is expected shortage. Now, what is value at risk, which is a very good risk measure? So, value at risk is just kind of mix of shortfall probability as well as expected shortage, but from the probability point of view. So, it talks about a confidence level or a probability, that for a given probability, what is the largest value of profit that ensures that the profit will be less than that value. Okay, so it's basically Let's assume again same certain line I have drawn it here, and let's say I have 95 or 90 confidence in my forecast. So for that particular part, I can say that let's say this is alpha probability here, this side, this entire thing, and this is 1 minus alpha. Okay. So for this 1 minus alpha, basically, so what is the largest value of profit, which is also a variable? So it is not predefined, this neta. What is the largest value of profit that ensures the probability of obtaining a profit less than this value will always have 1 minus alpha. So we will provide certain alpha or confidence in our expectation or the distribution. So let's say if you provided that, okay, I have 95% confidence in my forecast and like expectation. So 1 minus 95 will be 5%. So what is the value of this particular bar? So for 1% probability as being this cumulative probability, what is the value of largest profit? So this is like, there will be multiple profits below this neta value, but this neta value is the maximum profit, or basically you can say it is the boundary value where 1 minus alpha probability comes in. So that is the neta, and this neta can be defined as a value at risk. Now, conditional value at risk is basically what is the expectation for this confidence level for which the profit is less than this value at risk. So just like expected shortage, where this neta was, and sorry, sigma naught was predefined, here this neta is variable with respect to the confidence level, and then whatever is the expectation below this value will give you the confidence, basically conditional value at risk. So like, if I talk about all the values on this side, somewhat here can be the VAR. These are just, like for understanding point of view. It will depends how many scenarios are there on this particular side, and that will decide the exact value of the expected shortage CVAR. So CVAR is basically called conditional value at risk, and the condition is basically how much losses are basically happening, and sometimes we call it tail losses as well. Like at the tail, how much losses are happening. Okay. So these are basically different risk measures which we can discuss. Now, if you look at like, the our initial problem of like renewable self scheduling, how we can incorporate them. Okay, so we had some stochastic problem earlier, and if I want to basically incorporate variance and all, how can I do? So let's take this problem. Okay, so this is the one of the problem. Here what I am doing is I am assuming certain parameters here. So this particular problem I will convert. So this is a risk neutral problem, and let's convert it into a some generalized form. So it is basically sometimes, bilateral contracts are also present. So what we can do is we are maximizing the profit. Okay, and some x are like first stage variables. So these are basically here and now decision variables, plus some scenario, basically if we do some scenario summation over scenarios pi w, and then we have certain function, let's say a function which depends upon x and omega. Okay, so this is my another objective. Okay, so subject to some constraints. So like let's say x is set of some solution space, and then some ax plus b Y W are basically equals to some constant, let's say HW. So these are basically scenario based. So some equality constants are defined. So it is basically all the constants we can define it here. Okay. Now, if I just simply maximize this particular part, what I will get is I can solve it for very first is basically this C transpose X and simply solve it. And then we can solve that for the second stage variables. Okay. Now, like so far this particular problem has certain values and certain thing. Let's consider a particular example to understand different risk measures and how we can solve it. So I will just quickly move to a particular example, so that you can easily understand it. So let's say we have certain contracts which we have to make. So like earlier we discussed that there was one contract, contract A at that for the first time 3 hours, and then contract B for the second 3 hours. Now let's say for the entire duration we have an option of three contracts. Okay, one contract is, let's say, a certain price and quantity. Another contract also has certain different price and quantity, maximum quantity that it can avail. And third contract is also there, that we can obtain like certain quantity. So these contracts are also already there. Then we have certain scenarios that let's say different prices are there. In that case, if I want to maximize my profit, the profit will be, let's say, I have certain contracts, and we are solving it for let's assume for 3 hours. Okay, so t equals to 1 to, let's say, 3. So I have certain contract price and then certain contract quantity. Okay, so these are the here, and this contract is here and C decision. Then we have certain like variables basically. So let's say over certain scenarios we are basically trying to like so we want to maximize um, certain profit plus, okay, wait. So plus over different scenarios, let's say number of scenarios, and the pi w is basically the scenario probability, and then over t number of time periods. So this is also number of time periods, let's say. Okay, we are basically obtaining a lambda pool price or day-ahead price, I can call it. So let's say tw, and some quantity ytw is basically is being offered here. And yes, let's keep it ytw, that will be better. Then subject to we have certain quantity, like the contract can be have whatever is the maximum value of that contract. So earlier, like we had in the very first example 90 megawatt, and then we had I think 50 megawatt for contract A and 40 megawatt for contract B. So that can be PC max. Okay. Further, we can say that the this PC plus, like let's say we are talking about producer. So this producer wants to sell certain power. Let's say a producer example. So this PC he wants to sell in bilateral contracts, and this Y is basically he wants to sell in the pool market. So these are both of these should be basically PCT and plus YTW basically. Both of these should, let's assume, satisfy certain demand. So it should satisfy certain demand, let's assume. Okay, so then it has to be done for all time and all scenarios. These conditions has to be satisfied all time periods. Okay, then we can say another thing is this YTW is basically positive. So this has to be defined for all time and all W. So this kind of formulation is risk neutral formulation. Now, in this same formulation, I want to write it down, like I want to calculate the variance. How can I do it basically? So risk inclusion, if I want to do, what we can do is we can again write it down the same objective function. So it is again maximization of this objective. So it is summation over t equals to 1 to t lambda c and pct, okay, plus summation over omega equals to 1 to n omega pi omega and summation over time lambda pool price and y quantity in that particular price. So this is our objective first of all. So we want to maximize this. Then we want to minimize some part as well. So let's say minimization is, what we will do is we will calculate the variance. So how we can calculate the variance? So we will basically look at all the scenarios, one to number of scenarios, and to take the average, we can basically simply multiply the probability. So that can be called as a weighted average. Okay, and let's say this entire function is some function, okay, and which is dependent upon omega. Okay, if I assume that this entire function is dependent upon omega, so what I can calculate is basically I can put this value which is dependent upon omega minus, I will redo the summation over omega with the pi omega and this particular function. So I will get a this particular part as a weighted average, and then I will do a square. So this is how we can basically maximize the our profit or revenue and minimize the variance. So now just to understand it, uh, first of all we have to put some weight. So I have placed a weight that, okay, the 1 minus beta is the weight on the my profit revenue, and beta is the weight on my variance. So can anybody tell me if some function fw, like we are getting some value of function over the scenarios, what this part will give me? So let's say fw, or let's say f1, where w we are talking about, let's say 1 to 5. So f1 is, let's assume, 5, f2 is, let's assume, 3, and okay, let's keep it 3 only, and f3 is, let's assume, 8. What will be, and certain probabilities are there. That probability is, let's say, 20, 0.6 and 0.2. These are the pi w with respect to this thing. So what will be the summation over w pi w f w? It is 0.2 into 5 plus 0.6 into 3 plus 0.2 into 8, and you will get some value. Okay, if let's say all probabilities are equal, and if they are equal, they will be equals to for three players they will be equals to 1 by 3. Okay, so if all pi w's are basically equal, they will be equals to 1 by 3. And if I again further solve this particular value like w pi w f w, it will be probabilities are 1 by 3 into 5 plus 1 by 3 into 3 plus 1 by 3 into 8, and I can say it is 1 by 3 and 5 plus 3 plus 8. So this is nothing but the average value. So this probability multiplied with certain function gives you the average or mean value of fw. Okay, so this pi w multiplied with fw, this and then summation as well. Sorry, summation over w will give you the average value. So this is nothing but the average value. This is actual value. So this entire part is basically something like this: x minus mu whole square. Again, outside we are basically making another pi omega, or basically this another probability. So weighted sum is nothing but equals to 1 by n. Okay, and so this part is basically is variance. It's x minus mu whole square, average value of the x minus mu whole square. So this is nothing but the variance. So this entire function represents the variance here. So what we are doing is the above problem which we have discussed so far, like any problem, like whenever we have even this particular problem, like which we have discussed here, this risk problem. Let's for this wind scheduling, let's discuss it here. So this problem we had earlier, where over different scenarios we were trying to maximize the expected profit. Here this expected profit is function fx. Okay, and we can basically assume the entire thing as a fx, and once we can assume this entire thing as fx, we can calculate the var like this, that this entire objective function is considered as fx, and then we will put so just to like for the sake of simplicity, I do not want to write everything at the same time. This entire with all these summations will be placed here in fw, and then they will be placed here as well, and this is how we can calculate the variance in the objective function. And if we try to solve this particular problem and subject to all the constraints, like whatever the necessary conditions are basically we have defined, those constraints will also be there. If we try to solve this particular objective function, what we are doing is we are maximizing the profit and minimizing the variance. So this is how a risk informed decision making can be done. So if we are doing this kind of formulation where risk measures are part of objective function, and that is basically we are including the risk, and they are no longer risk neutral. That they are not looking at the risk was no longer exist, and we are looking at the risk value, that what can be the risk value. So here, like, one of the modeling is for the variance. So this is how we can model the variance. And these betas are basically how much weightage you are you want to give. So for, like, different beta values, these coefficients, these are constant. So if I assume 0.5, it means 1 minus beta will also be 0.5. This is also 0.5. So I'm giving equal weight to the my profit as well as the risk. If, let's say, beta value is 0.1, then it will be like, profit weight is 90% and risk minimization weight is 10%. So it is basically a multi-objective uh, problem. And you know for multi-objective problem, for different values of betas, you will get a Pareto front between the uh, profit, expected profit, which is this first part multiplier of 1 minus beta, and then variance, which is the multiplier of beta. So you will get different, basically, a Pareto front. And based upon, like, how much a risk loving decision maker, or let's say, in this particular case, producer is there, he can make a decision that, okay, this will be the schedule for the our renewable schedule for the next day. Like, the outcome again, for the same renewable scheduling, we can do this thing, and the outcome again will be the, like, what will be the schedule for the next day. If you have any questions, please ask. Mohit. Yes, do you have any question? Please ask. So, if you can, like, get, so whatever about, if you want to learn more about uh, risk modeling and uncertainty handling, and like, how to do solve stochastic, like, learn about the stochastic process and stochastic programming, I will put a book for your reference in this particular notes. Let me see if I can paste it somewhere here. Yes. So this is a book which is available. Okay. And we can basically, you can, if you have access from your library or somewhere, you can use this particular book. Okay. So this is a book, Decision Making Under Uncertainty in Electricity Markets, and authors are basically A.J. Konyo. Okay. So this is very good book, from where you can basically uh, refer all of these, and there are a lot of uh, formulations are provided for renewable wind power producer, and like, retailers point of view, producers point of view, consumer point of view. So different formations are available there. So if you want to learn more about uncertainty, how to handle uncertainty, and how that decision makers make decisions under uncertainty, you can follow this particular book. So I would recommend you can, if you have get access for this book, do it. Okay. So if no questions are there, we will basically end our session today. And Thank you. One more thing is about your quiz basically. So there are some questions which was descriptive type. Okay, so those questions, like I have just seen a few of the response. Let's say like the question number one, like how what was the objective and for the deregulation. So the answer was like there can be multiple answers. So in the quick response which you must have obtained, uh, most of you are basically getting 0 marks in that question, but do not worry about it. Like I will go through each question and I will read it, because it's auto corrected quiz. I have not corrected it so far, so I will correct each and every response and update the scores on the Google like quiz. Okay, that's it, I think. Thank you very much. I again reiterate myself, if you have any questions, you can also email me. Okay.